Welcome back to another edition of TEC Tube. I'm your host, Ryan Hoger, and today we're going to talk about heat pump balance points. We'll cover it both from a perspective of an all-electric system as well as a dual fuel system where we combine electric heat pump with another fuel source such as gas, propane, oil, etc. There are two balance points involved in these discussions. There is a thermal balance point, which means at what outdoor air temperature can the heat pump that I selected no longer keep up for the building that I'm putting it in. And then there's an economic balance point, which is what is the outdoor air temperature at which it's less expensive to run my non-heat pump thing. Stove, furnace, fireplace, whatever you happen to have, right? That's not electric related. So I'm gonna pull up some slides here to kind of illustrate this for you guys. We're calculating these balance points. There's a couple things that I have to know. So the first thing I have to know is the load of the building, the heating load of the building. All right, so I'm gonna use a house in my example, but it would apply to a commercial building as well. I need to know the heat load or the heat loss of the house. You have to be real with this. I know everyone oversizes everything, like it's bad, right? And I have other videos on the oversizing problem, right? But you have to not oversize it for this. Even if you plan on putting a 4-ton system in at somewhere that only needs a 3-ton, you have to do the real load calc. Otherwise, all your answers will be jacked up and it'll be all a waste of time. So you have to take all your safety factors out of the load calc. Don't put in a fake outdoor air temperature. Use the actual weather data. Like, oh yeah, but where we live, it gets down to -10 sometimes. Yeah, but your design day's 2. Use the 2, right? Don't fluff everything, right? So get a real load calc, and you could always tweak things later if you want, right? And then you need to know the model of the heat pump that you're gonna be using and go find its data. So for every model of heat pump, and I have a generic one right now, but I'll show you some specific ones in a minute, there'll be a graph like this, or it could be a table with a bunch of data. But there'll be a graph like this. And in my case, it's showing me on here, let me get a little laser pointer thing going. It's showing me 5-ton, 4-ton, 3.5, 3-ton, etc. Right? And there's a graph here, and it's outdoor temperature along the bottom, and it's the BTU capacity on the other side. And these lines represent how much heat the heat pump can move from the outdoors to the indoor. These are all air source heat pumps, right? So how much heat can it take from outside and put into the inside? And obviously, as it gets colder outside, it can do less of that. This red line I've added to the graph, and this represents the load of the building in question. So I did a load calculation for this house. It was 55,000 BTUs on a 0-degree day. 0-degree day is our design day. Actually, 1 is the design day for this community, but 0 for discussion purposes. Right? I know it gets down to -12 once in a while, right? But I'm using the actual design day. So 55,000 BTUs are needed on a 0-degree day. And then what I do is I figure out when does the house need no heat, right? This is an existing house, and I know they shut their heat off at 52 degrees outside, which is a little bit on the low side for a lot of people, but it's a pretty tight, good house, right? If for some reason they shut the heat off at 65, I would end my curve over here, right? So for example, if I add that line, it won't be very straight, but I'll do my best. If I took 65 degrees, I'd take a line from when they don't need heat, and I draw it to where it's 0 degrees, or where it's heat loss time. So in that case, my balance point would have been 35 degrees. In my case, since they shut their heat off at 52, the balance point was 30 degrees. This is the thermal balance point. This means below 30 degrees for that exact property with that particular model of heat pump, they do not have the ability to heat it with this heat pump alone. They need help. Specifically, something has to heat this section right here. These days. The heat pump can help me down here, but over here, something else, gas, furnace, electric heater, somebody has to bail me out, right? This is specific not only to the house, but the model of the heat pump. So if I picked the exact same house and gave it a different heat pump model, so now I'm working with something totally different over here, but it's the same house, 55,000 BTUs on a 0-degree day, 52-degree day, I don't need any heat. For this one, it's 20-degree thermal balance point instead of 30 degrees. Right? And one more example here. For this one, I'm at a 26-degree balance point. And I could have also upsized and put a 4-ton instead of a 3-ton in, and then my balance point would have been 17 degrees. So it depends on the model of the heat pump, the tonnage of the heat pump within that model, and the load of the house. That'll determine what your thermal balance point is and when you need to have some other heater kick on. Now, if you have an all-electric system, meaning your auxiliary heat is electric resistance heat, the heat pump is pretty much always more efficient than electric resistance heat. So you'll never shut the heat pump off. Even when I get down to that thermal balance point, I keep running the heat pump and I add the electric heat as a second stage to help it out, right? If I have something other than electric heat as my auxiliary heat source, that's when things get more complicated, because now I'm not paying for electric and electric, I'm paying for electric and gas, or electric and propane, or electric and whatever other fuel you have. So that becomes a little bit more challenging on calculating that. We call that the economic balance point. Just to give you one more example on that, that's that same graph we saw a minute ago, but I'm taking the table data from another heat pump, an inverter in this case, and I'm overlaying that on the graph just so you can see, hey, this is what happens when I have this model versus this model. And it makes a difference on that balance point, all right? To find the economic balance point, I need to know the cost of gas and the cost of electric, right? So to do that, what I personally do, since I live in one of the communities that would be the same place that my company works in, what I do is I look at my own bills. So I'm gonna use 2024 since this is the last complete year that I had. It's 2025 today. For my gas, I was paying 94 cents a therm. Now, if you look at my bill, it says I'm paying like 38 or 40 cents a therm. But then I have distribution and delivery charges on top of my supply charges, and I have taxes and fees and all these different things. So what I do, because I'm a nerd, is I take my total therms each month and I divide it with the bill cost. So I get dollars per therm. So 133 divided by 172 is 77 cents a therm, right? For the whole entire year, I paid 94 cents a therm. I do the same thing for electric. My electric rate is 6.69 cents a kilowatt hour. But once I take in my delivery charges, taxes, and fees and everything, I'm paid 17.9, more than double. So you have to really do it that way to know what you're actually paying. So 94 cents and 17.9. For discussion purposes, I'm gonna show you in a second what happened in 2022. My gas was $1.31 and my electric was 13 cents. It was kind of flipped from what it is last year. So that does in fact make a difference. So if I go to that same chart that we had a second ago, I get this one from Minnesota. I actually have to stop using it because I pay more now. But if I was only paying 16 cents instead of 18, and I had 90 some cents for my gas, that would be a 60-degree economic balance point. Meaning when it's above 60 degrees, you would use the heat pump, and below 60 degrees, you'd use your gas furnace in this case, which basically means never use the heat pump. When your electric rates are that high and your gas rates are that low, there's no reason to run the heat pump at all. Just stop using it, right? Now, if your rates are different, then it's different math. Or if you got solar panels or something, different math. But for this straight up gas versus electric example, that would be the case. Now, if I go back to that other example, 2022 year, I was at $1.31 and 13.2 cents. So $1.31, I'm over here, where's my laser pointer? I'm over here, let's call it $1.33 and 13 cents. 35 degrees is my cutoff point. That means above 35 degrees outdoor air temperature, I would run the heat pump, and below 35, I would run the gas furnace. All right, so it does matter what your utility rates are. That's the biggest factor. Utility rates are the biggest factor in the economic balance point. The efficiency of the equipment, not so much. Thermal balance point, the efficiency of the equipment's a big deal, as is the load of the house, but economic balance point's mainly utility rates. If you want to be more specifically detailed about calculating this, as opposed to just pulling up a random chart from Minnesota, you can use this formula here. I got my calculator ready. So in this example, you're going to calculate the COP, coefficient of performance in the heating mode, at which you are the economic break-even point. So what's my utility rate? This example was 13 cents for electric, and I was $1.15 for gas, and my furnace was 92% efficient. So the formula is the price you pay for electricity multiplied by this conversion factor from electricity to gas, multiplied by the efficiency of your furnace, divided by your gas rate. And that came out to be a COP of 3.1. If I go look at a heat pump, for example, the one in this table right here, 3.1 would have meant 35-degree cutoff point. Above 35, run the heat pump. Below 35, run the gas furnace. If I recalculate that with my current costs, right? So if you recall, I was at, I think it was 18 cents for electric, times the 29.3 unit conversion, multiplied by let's give the benefit of the doubt. Let's say I have an 80% furnace. I have like the legal worst furnace that I could possibly install. And my gas was 92 cents. Oops, 0.92. 4.58 COP would be my balance point. 4.58 puts me at like 80 degrees. In other words, don't turn the heat pump on this year at all. It makes no sense whatsoever. So you can calculate that on a case-by-case basis to decide what you want to do with that. If you don't want to do math, some of you guys are Bryant and Carrier dealers, and there is a software tool on HVAC Partners that you can navigate to for Carrier and Bryant, and you can put in hybrid gas heat and then pick your model number of heat pump and whatever kind of furnace you want. In this case, I have a 90% furnace with a 15 SEER 2 units, and it'll calculate the thermal break point and then economic break point. In this case, the thermal break point was 29 degrees, meaning below 29 degrees, the heat pump needs help. And my economic was 62, which by the way is the highest this software will calculate. It doesn't calculate anything higher than that. Just like the Minnesota chart I showed you doesn't show anything higher than 60 degrees. It's like, why bother keep calculating this? Because it basically says don't run the heat pump. And this was based on 94 cents and $1.18. If I switch it to 13 cents and $1.31 for that, right, I'm gonna get a new calculation on there. Right, and now it's saying my economic break point is 18 degrees for this specific model. So it's very dependent on your electric and gas cost. Where we live in Northern Illinois, ComEd and Nicor, 2008 and 2022 were great years to run a heat pump and turn your furnace off. All the other years, the furnace has pretty much been the winner. But hopefully that helps you calculate these things, and you can program that changeover point into your thermostats.